Okay, so let's pick up here where we left off on the second part of 7.2. Just go over a few different examples using our new derivatives and integrals. So here's what we have so far. Up to this point, we've discovered that the derivative of the natural log of x is 1 over x, and the derivative of e to the x is e to the x. And that means that the integral of 1 over x dx is the natural log absolute value of x. The reason for that absolute value is just kind of to extend the definition of that indefinite integral across all values of x. All right, and again, e to the x, the integral of that is back to the same function, e to the x. All right, so, and again, rules like the chain rule will still apply. So, for example, let's take a look at examples here. All right, so let's say my goal was to find the derivative of this, right? So again, remember chain rule says derivative of any exponential here is just going to be the exponential itself. So you just rewrite it, and then chain rule says take the derivative of the function that we have up here, right? X squared plus 1. And the derivative of that is 2x. So we get 2x e to the x squared plus 1. All right. And then the same for if we had all right, it's always here the derivative of any natural log function. It's 1 over whatever is in the argument. Leave it as is. And then times the argument there, sine of x, which the derivative of that is cosine. All right, and that is cosine x over sine x, and also known as cotangent of x. All right, so that's kind of how you would approach derivatives. Now the integrals, so example, so far I think the only technique at this point covered in Math 1 was substitution. All right, and then so in the next chapter we'll learn a bunch of other techniques to integrate. But for now, let's say that our goal here was to evaluate something like this. All right. Okay. And now we could see, okay, so this is not a basic form, but a substitution will lead us to the answer or the evaluation of the integral. All right, so my substitution, I'm going to let u equal to x squared. That means du is 2x dx, right? And I see the x dx out there. The only thing I don't see is a 2, so let me divide that out. All right, and now we have our substitutions. All right, so now going to our integral here. This is equivalent to x dx gets replaced with 1/2 du e to the u. And now it's our basic form, right? The integral of e to the u is just e to the u. Don't forget the plus c. And then substitute back our variable in terms of x. All right. Okay, so now that's how we can use our integral. Now, the natural log integral, in other words, our basic form 1 over x, the integral 1 over x is the natural log of x. That leads us to be able to integrate a whole new set of functions. Right now, if you recall up to now, right, with what we've learned in our first semester calculus, this was not a basic form, right, of integrals, right? Looking at that, we just didn't know how to do that. But now with our natural log, right, I can actually solve this type of integral. Right? So I'll start off by, here we'll have sine of x over cosine of x dx. All right, and then I'll use a substitution. All right, so I'll let u be equal to cosine of x. All right, the reason for that is it looks like I see the derivative of cosine is negative sign, and I see the sign in the numerator. So the goal here is to get it into the basic form 1 over u here by applying this substitution. So that means that du is equal to negative sine x dx. Now there's no negative in there, so let me multiply both sides by negative. And we get this. All right, so now I have everything to substitute here. So sine x dx, right, that gets replaced by negative du. And cosine, remember, it's in the denominator, so 1 over u. Okay, and now 1 over u is negative natural log of u plus c. Doing some back substitution, u is cosine of x. All right, and then this is just doing a little simplification here. Remember, the coefficient of the natural log becomes the exponent. Be careful here with the notation. I write it like this because keep in mind when we write cosine to the negative 1x, that is referred to the inverse of the cosine, right? And here it's not an inverse, it's the reciprocal, right? 1 over cosine x, which happens to be the secant of x plus c, right? So this natural log integral brings up or allows us to integrate a whole new set of functions that I can, if it's not already in that form, that I can do a substitution so that it is in the 1 over u type, so I can apply the natural log, right? Okay, before we move any further, I do want to just clarify here one thing about this inverse notation, right, is that when you see this, this is inverse, not a exponent. It is a bit confusing here. If it were any other number, we would interpret it as an exponent, but in this case, we do not. Right? So keep in mind, when you see something like this, this is inverse cosine. Okay? And then when you see something like this, like I had up there, this is 1 over cosine x, right? All right, so just be mindful of that. I see a lot of confusion in this, kind of how we interpret that. Okay, so just be mindful when you're working through problems and you come across this notation. Okay, so those are our new integrals and derivatives. Now we can also find inverses So let's say that let f of x equals to 1/2 natural log of x minus 1. And let's say I want to find f inverse of x. Okay. So again, for something like this, the first step is, let me write it in y notation. All right, so again, y is equal to f of x. And then from here, let me swap out the x and the y. So this becomes x. Okay, all right. And then from here, the goal here is to solve for y. All right. Okay, so here we have solving for y. We get, let me multiply both sides by 2. So we get 2x equals to natural log of y minus 1. All right. Now, since the exponential and the natural log, well, the exponential is a one-to-one function, we can essentially, what it amounts to is take the, or raise everything to the e power, right? Or e raised to the, if this is true, then this is also true, right? And the reason for that is because e to the x is one-to-one. All right. Okay. And now, knowing the inverse relationship between e and the natural log, this becomes y minus 1. And then we add 1 to both sides here. And now we have found f inverse of x, that equals to e to the 2x plus 1. All right. So that is how we would find an inverse involving a natural log, and we use, if it was an exponential, then we would take the natural log of both sides to kind of solve it in that way. All right, so let's try, how about another example here? So for this one, let's do where we're finding the equation. Of the tangent line to the curve y equals to e to the x over 4 minus x at the point 0, 1, 4. Okay, so this is a problem that we would encounter in our first semester calculus course, right? Find the equation of the tangent line. Okay, so so what do we need to find? In general, the equation of a line, we need a point and a slope. All right. Okay, so we have a point. We're given 0, 1/4. All right, so now the next thing I need is a slope. Now, how do I find the slope of the tangent line? That involves a derivative. So let me find y prime. Derivative of e to the x is e to the x. Derivative of x is 1. All right. And now let's evaluate that when x is equal to 0. All right, and then e to the 0 is 1. So we get 1/4 minus 1. That equals to negative 3/4. Okay, so now we have our slope. Excuse me. All right, so now we have our slope. And let's put this together to find the equation. The equation using the point slope formula. All right. Okay. And again, that 1/4 and the 0 is the point on the line, and then just kind of writing it in slope-intercept form. And we get that. So that is the equation of our tangent line. And here we can see, let me show you a graph of the function itself. That function is the one in blue, and in red, what you see there is the tangent line. Okay, so there's an example finding the equation of a tangent line. All right, so okay, so now another application here. Let's say let f of x, so another example here. Let f of x equal to x plus 1 to the 3/2 times x minus 4 to the 5/2. Okay, and here we have 5x plus 3 to the 2/3. All right. Okay, and let's say that we were asked to find f prime of x. Okay, so looking at this, we would say, all right, this looks like a really tedious problem. We would have to use the product rule along with the quotient rule, and then for the denominator, the chain rule as well. So we would say, all right, that looks like a very tedious task to actually do. And not terribly hard in terms of the concepts, right? We've covered the concepts before, but it just looks like it's very tedious. Now, when we have something like this, remember, what does the natural log do, right? We're going to introduce it to help simplify our problems, right? And we can see why the natural log can be very useful, right? Because what does the natural log do? It takes multiplication, changes it to addition. It takes division and changes it into a subtraction. So let's use that. The nature of the logarithm is that it's 1-to-1, so I'm allowed to essentially use it like an operator where you can say, take the natural log of both sides. The 5/2 to the 2/3. Okay, and I'm going to work with this function to find f prime. Remember, the goal is still finding f prime of x. Okay, so before I start taking derivatives, let's actually apply all of the properties of a logarithm. Okay, so here I'm going to do this in one step, so just kind of keep up with what's happening here. All right, so the numerators I can write as being plus right? And remember, if it's an exponent, I can now write it as a coefficient of the natural log. And then plus, right, ln of x minus 4, and that exponent can now become a coefficient. And now the denominator, remember, the division gets changed to a subtraction. So minus 2/3 natural log of 5x plus 3. All right, that 2/3 becomes the coefficient. All right, and now, as you hopefully start noticing, this one is a lot easier. I don't need the product rule. I don't need the quotient rule. I just need the derivative of the natural log, which is really 1 over that function. So now let's take the derivative of this, right? Now on the left side, Here we're going to use implicit differentiation, right? 1 over f of x, and then chain rule, right? F prime of x, right? Some unknown function, which I'll actually find in a second. All right, and then over here we'll have, okay, this becomes, that's just a constant, so let me take the derivative here. 1 over x plus 1. Same thing here. This just becomes a, that's just a constant. So derivative of ln of x minus 4 is 1 over x minus 4. All right, times that 5/2. All right, and then for the last one here, I have, okay, here we'll have in the denominator 3, 1 over, now here's where we have to be careful. All right, so 1 over 5x plus 3, but what does the chain rule tell me to do? Times the derivative of the inside, and what's the derivative of the inside? 5x plus 3, the derivative of that is 5, so times 5. All right, and now we can solve for f prime of x, right? Multiplying f of x to both sides of the equation here, we get 3 over 2 times x plus 1, 5 over 2 times x minus 4, and then minus 10 over 3 times 5x plus 3. All right, and that f of x is simply this function here, right? Which I won't write, but remember that's just referencing this f of x. All right, I'll just write it in a more compact form that we have there. Okay, and I noticed that made a lot of the work less tedious than if we were to go ahead and actually try to differentiate here at this point using quotient rule, product rule, stuff like that. All right. Okay, let's try one more example here, taking a derivative. Okay, so how about we want to do something like this. Okay. Now, something like this, we actually don't have a rule to do something like this. Okay, so I want you to kind of look at this and then ask yourself, is this a power rule? No, this is not a power rule, right? Again, because the power rule applies for power functions. This is not a power function, right? So the power rule, let me use a different color here, applies to functions x to the n, right? Where n is any rational number, or really any real number, as we've seen here, right? That is not what we have here, right? The exponent is, in fact, containing the variable. So we cannot use the power. So keep in mind here, when you see this, please, I can't, very common mistake that I see all the time. You see this and you're like, oh, power rule, and then maybe a chain rule, but that is not what we have here, right? So keep in mind that this does not apply. Okay, and in fact, I don't think we've, at this point in our calculus sequence, we have not worked with differentiating functions that have a variable in the exponent. All right, so what I'm going to do here is, well, what if it wasn't in the exponent? What if it was instead a coefficient? Well, how do I do that? Well, those are one of the properties of the logarithms, right? We could say, okay, let me start by getting that variable out of the exponent. And one easy way to do that is by taking the natural log of both sides of the equation. And now, using properties of logarithms, I can bring that exponent as a coefficient. And now I can take the derivative of this. All right, so now I can find f prime of x. Okay, so taking the derivative again on the left side, using our implicit differentiation. On the right side, we're going to use the power rule. All right, so there's two functions here, right? You can think of this as one function and this as another function. It's a composition of functions, but it really is just one function, that natural log, all right? Just keep that in mind. All right, it's not two separate functions, it's a composition which yields one function. Okay, so let's take the derivative of 2x, which is 2, leave the other function alone. Now leave 2x alone and take the derivative of this. Remember, always the 1 over whatever is the argument of the natural log. That's the first part. Chain rule now. Work your way inside and take the derivative of 1 plus 1 over x. And that turns out to be negative 1 over x squared. Okay. There, the power rule does apply there. Okay, so let me, from here, let me multiply both sides by f of x to kind of get rid of this here. So multiply with another space here. F of x, and then on the left side we have f prime of x equals to, and here I'm going to do a couple things. So I'm going to factor out, they both have a 2, and since I've now multiplied by f of x, and then in the brackets we'll have natural log of 1 plus 1 over x, and in here the algebra we have minus the 2 I factored out, the x over x squared, so one of the x's simplify, and then I'll multiply the other x in the denominator with that denominator there, and we're left with x plus 1. And that is the derivative of f. And again, f of x that you see there can be replaced by that function up here. 1 plus 1 over x raised to the 2x. All right. So that concludes section 7.2. Thank you.